So now we're going to look at another application of max flow. So in this situation, we have two companies, company S, who supplies goods to furniture stores, and then company D, which is a furniture store that wants to build furniture. And in particular, company D needs to use supplies from S to build its furniture. So in general, we have a bunch of furniture items, I, that D produces, that requires some set of components to be bought from S, and such a furniture item I will bring company D profit DI. So if D decides to produce a set X of furniture items, it obtains profit for each furniture item it makes, but it has to also pay S the total cost of acquiring those components needed to build those specific furniture items. So the goal of D is to maximize its net profit, which is this. So this is exactly the project selection problem. So from D's perspective, we have this dependency graph with a bunch of furniture items. So there's M furniture items, and then for each item there are certain components that it requires. So we have also N components, 1 up to N. And for each furniture thing, we have some number of components required to build it, and then for each node we get some profit, P1 to PM, but these components have a cost C1, C2 to CM. And so our goal is to choose projects, which here are furniture items to build, so that all the prereqs are met. Here the prereqs being you have the supplies needed to build that item, and you want to pick the total set of projects that maximizes your profit, which is how much money you made from the furniture minus how much you had to pay for the supplies. So from D's perspective, it's just a project selection problem. So if D knew the costs, it could just do the selection reduction on this graph that I just showed you there, which I'll call G, and that will take O of V times E time from what we know from class, because it can be solved with min-cut. So cool, so from D's perspective, we can solve this problem efficiently, and in particular, this O of V times E is going to be something like O of the number of vertices is N plus M, and then you might have all possible edges, so this is like N plus M times N times M. So that's your running time in terms of the original inputs. So assuming N and M are roughly the same, then this would just be O of N cubed, to give you an idea of what this looks like. Okay. Now that's from D's perspective, but that was too easy. So in this problem, you are hired as a consultant for company S, and you want to pick these prices of the components. So you're picking these cost of J's. Now, if you set the prices too high, then company D is not going to buy anything. So obviously, we need to pick these prices, these costs, so that company D would still profit. But it might profit very little, just barely above zero. So your goal is to come up with these prices that gives company S the most profit, but still encourages company D to build stuff. So basically, you're going to pick the cost of J for each component J so that the best profit D can make is barely above 0. So we'll just say it's exactly 0 to make it simple. So if they profit a total of 0, we'll assume they still buy the stuff. So you want to maximize the costs, which corresponds to your profit, so that D will still attempt. So your goal is to maximize your own. You're maximizing the sum of the cost of J's subject to D still profits from them. So that's your goal. So essentially, the way you do this is to make the cost as high as possible so that D barely profits. So how are we going to do this? Well, we know that D is solving a project selection problem once it has the costs. So we're going to use that to our advantage. So if we remember what the project selection reduction looked like, we have S has edges to each of these 1 through M with the profit values. Technically, we also have edges to the components, but we already know those don't profit us, so there's no point. Then we also have the 1 to N components. We have edges of infinite capacity whenever there's a dependency. And then at the very end, we have T, and we would have the cost will be on these edges. So that's in the original. So now all we're going to do is make these infinities to represent that we're going to increase these costs as much as possible. And if these are as big as possible, then we're maximizing our profits. But still, because it's a project selection problem, it's still going to find a min cut, and that's going to help D make its decisions. And notice the min cut here, which is also the only feasible cut, is this cut. So in particular, what will end up happening is the sum of the costs will end up being exactly the total profits. So you'll design the costs so that company D tries every possible project and makes nothing, and so you'll make as much as you possibly could. So i.e., costs are low enough so D attempts every project, or attempts to make all furniture, all M items, but high enough to where they get 0 profit. And obviously this is the best you could do as company S, because if you made this any bigger than the sum of all the profits for company D, then immediately they would get a net negative profit from doing this. So clearly we can't do better than this, and so this will be maximal. So the main reason we're even considering the flow network is because we need to construct these. So just by considering the network, we can immediately figure out the most profit we could make, but the goal of the problem is to actually come up with the profits, not just the number. So if we just wanted the number, the best profit we could make for company S, it's going to be this. This is the best company S could do. but this doesn't actually tell us what the prices are. So to do that, we're going to actually construct the graph, the project selection graph, but with the new infinite capacities, and then run max flow, and then whatever the flows are on these edges become the prices. So ultimately, what's the alg for S, for company S's perspective? Well, they're going to build the project selection reduction graph. So I'll just call this G prime. But with the infinite capacities, so we build that, and then we just run max flow. Specifically, we'll use Orland's. Because again, here, these prices and costs could be very, very high. So then finally, the price, or we'll say the cost of item J, that's just going to be equal to the flow that we compute it'll exactly be the flow from J to T. And the total profit that company S gets from this will be the sum of company D's potential profits. So overall, this is going to be the same running time as this. So it's still n cubed. If n equals m. And that's just because ultimately we're just running the same project selection algorithm, just on a slightly different graph, and then returning the flow values. Okay, so that's the entire algorithm and the analysis. So the only question here is correctness, but correctness is obvious by this argument here. We know by the project selection algorithm, we know this is what's going to happen, and that's correct. So from D's perspective, this is the only cut, and so that's how much, that's the total capacity they'll get, which ends up giving them a net zero profit. And we already know that obviously they can't get more profit than that. They couldn't get more profit than that because then company D gets a negative total profit, and so they won't even try to buy company S's products. So clearly this is going to be the maximal thing. That's the most they could possibly squeeze out of D. And then by the construction, we know the amount, the net amount leaving S is the net amount entering T. That's just a property of flows. And so if we just take the flow amount to be the costs, we're actually maximizing company S's profit.